Yeah. So here we are going to look at the application of multivariable linear regression. And I know that you have some, you've learned linear regression, the simple linear regression, a number of times in many courses in statistics, even in secondary school. So in those lessons, you learn how to calculate linear regression or develop the model using a calculator and pen and paper. But when it goes to multivariable linear regression, that means linear regression that involves multiple variables, then it's more difficult, or it gets more and more difficult for us to calculate by hand and using pen and paper as well as calculator because of the number of calculations required. So this use tools to help us to calculate those parameters for us to come up with the model multivariable linear regression. So far, so good. Everybody can hear that?
Yes, doctor.
Loud and clear, right? Okay. So I'm just going to go through very quickly what we're supposed to learn in this very short one class or one engagement on the topic. And these are the learning outcomes for just this 1 hour or this 50 minutes. At the end of this class, the students should be able to not really to perform linear regression, but then at least be able to know the general idea of how do we approach linear regression, multivariable and linear regression in Matlab. And that's why I mentioned here, you'll be able to explain the steps to perform linear regression for two variables in Matlab, because the simple linear regression that we learned before in other courses are just the two variable linear regression, X and Y. But how do we do it in Matlab? I think I might have touched this a bit in IEA 216, but maybe we haven't gone into that much detail of the steps. Although for this class, we're not going to go that much in detail too. It's just that I'm going to show you the steps on how we can perform linear regression in Matlab. Number two is be able to explain the steps to perform multivariable linear regression. So this is the main topic of the day for this class. But this is going to be for three variables, because anything more than three variables is going to be difficult to visualize. So on the right here, you see the linear regression model or the output of Matlab. The linear regression model output of Matlab, and also the plots of the points. So this is the linear regression, while the second one here is the second figure at the bottom here is the multivariable linear regression output. Notice that we are still able to visualize 3D data in this form, but anything more than 3D, or that goes to 4D, 5D, and 6D, then we're not able to visualize it, but we can still use the same steps to develop the model. The only thing that we cannot do is to visualize it. So that's why we are stopping at just three variables, but just keep in mind that it can extend, using the same steps, it can extend to other more variables, more than three variables, 5, 10, even 100, 200 variables. And then you'll be able, third learning outcome is you'll be able to explain the steps to plot the data and model. So this is the two plots. We'll also cover this a bit, although you did study this in IE 216 before, but I think it's good for you to be reminded of what you can do in terms of plotting in Matlab. So far, so good?
Yes, doctor.
Yes, doctor.
Yeah, just tell me if my voice cuts out or it becomes soft, because I have no way of knowing it unless you tell me. I hope you're not that shy about that. Okay, so these are the topics, very simple because we just have 50 minutes. One is linear regression in Matlab, and the second is multivariable linear regression, also in Matlab. I'm going to show you the Matlab screen from now on. There's no more PowerPoint screen, so you can follow along with me, the code that I type. If you have your own installation of Matlab, it's good, so you can follow along. If not, then I can pass this recording to you for reference if you want to follow along at a later date or a later time. Okay, now let me share my Matlab screen. Okay, can you see this two window?
Yes, doctor.
Yes.
Okay, one is the workspace, or I guess the default window of Matlab. We have, I hope you still remember this, we have the current folder, the workspace, and the command window where you type in your commands here. And then there is the script window here, where we write all the comments that we need to run the analysis, and we click on run for it to run all at once or in sequence. I'm going to use both of those. So let's start off with linear regression because that's the first topic. So how do we perform linear regression here? Now, I want to talk about linear regression, although I'm sure you've studied this many times, but I just would like to open it with linear regression so you can appreciate multivariable linear regression. Because the difference between the two is just for linear regression, simple linear regression is just two variables, y and x, where you plot x versus y versus x, and you plot the line that best fits the points in the plot. For example, like this one just now I showed you. Let me just increase the size. Where we have the x and the y, and we plot it in the scatter plot, and we draw the line that best fits the data. So this is the simple linear regression. And then when you are reminded of that, then it's easier for you to appreciate the multivariable linear regression that goes above two variables. So let's try to work on linear regression first. Let's run a script of the steps. Let's run the commands to run linear regression using a sample data set within Matlab. Maybe I didn't cover this in I216, but in the previous course, computer applications, but just so you know, there are sample data sets in Matlab for us to test our code. So we don't always have to add in our own data every time we want to use Matlab. Okay, first of all, am I going too fast, or I'm going just nice at a comfortable pace? So that data set, the sample data set that you can use in Matlab is simply this command. You just use load, and you need to know the name of the data set. The data set that we are going to use for this example is the accidents data set. So Matlab has in it sample data sets, many data sets, and one of them is accidents. And I'm just going to use this for the example, and it's also available as a tutorial in the Matlab website. So once we load this, you notice that we have all this data already loaded in our workspace. When associated with the accidents data set is this data sources value highway column. I think I'm not sure what this means. HWY stands for highway, COL, I think maybe columns, highway data, highway headers. So something to do with accidents that occur on highway, and this is probably in the US and not in Malaysia. So if we double click on this, then we get to preview what they are inside each of these variables. Okay, so this data sources will be here. I don't think this is that interesting. Yeah, these are the sources. US Department of Transportation. And then highway columns. Oh yeah, this is the number of columns available in the data set, 17 columns. Highway data, this is the actual data, column 1, column 2, column 3. It doesn't tell us what they mean, but we know there are 17 columns. Maybe later we'll find out what they are, but we're not going to use all of the columns. And then the highway, okay, this is the meaning, the highway headers. The first column is census ID, the second column is centroid longitude. I think this is the locations of the rows of observation. Column number 4 is traffic fatalities. I guess this is one of the limitations of Matlab. Not really limitations, but disadvantage. It's just the way that they set up in Matlab. I think because they want to use the matrix setup, because Matlab is made up of is originally developed for matrix. So they don't name the headers, they maintain the numbers for the columns and rows. So in other software, like say in Excel or in R, then we can actually name the columns, but inside Matlab, they have to separate it into another variable to tell us what the headers are for each one of these columns. And then the highway ID, I think I'm not going to go through all of this. So I think the most important is this highway data, and then for the highway headers, it's just for us to know what they mean. Okay, so enough with that. Let me close this. Okay, so after we load accidents, then we we're trying to demo linear regression, so we need to have two variables. So I'm going to name the first variable X, and then I'm going to take it from the highway data, this one, and I'm going to take all of the rows, but for column number 14. Okay, and I put a semicolon at the back to suppress the output. And then after I define this, I have my X data there, 51 rows. And then I believe this 14 here, if I look at the highway headers, it should be this one, total population, all right? So this is total population, and then Y is equals to, again, we take it from the highway data, and we're going to use the fourth column. Okay, what is the fourth column? Let's look at highway headers. Oh, traffic fatalities. Okay, so which means that we're trying to find the relationship between, or to find the model, the linear regression model between population and population here and fatalities, whether there are any, if there's an increase in population, are there increases in fatalities. And this is not part of the code, but never mind, let me just show you what the plot looks like between the two. So I'm sure you still remember, if you want to plot X versus Y, it's just plot X versus Y like that, because here's X and here's Y. So we plot X and Y, we already defined them, it's already here. So when we press enter, then the plot window should come up, and then you should see the plot. So on the x-axis is the population, and the y-axis is the traffic fatalities. So far, so good, everyone?
Yes, Doctor.
Okay. Next, we are going to build a model. So how do we build the model? Okay, I'm going to type format long. Okay. Okay, before I type format long, let me just show what it means by that command. We're going to define the coefficients of the model. Let me just write it here. You know that for a linear regression model, it's something like this, right? And m is a coefficient, c is constant, and but then usually we would not type it like this. We would type it like this: b naught plus b1 times x. And b naught here is the what do you call that? Y-intercept, while b1 here is the what do you call that? The slope, right? So b1 here is m, and b naught, b0 here is the c here, the constant. So this is just the standard way of writing linear regression model, although we are used to writing the linear equation like that. So b1 here is the slope. So what we're doing right now is calculating b1, and to calculate b1, that slope value between the two data is just x backslash, I think this is backslash, right? Yeah, this symbol backslash y, and when we press enter, then we get the value here. It's 0. See, e to the power of -4, which means it's a 0.00. I'm just gonna type it here, which means it's 0.000137 etc. Plus it's e to the power -4. Now, just now I wrote the first code format long, means that you want to see more values of it. So if this long here means that we want to see let me try it first, but it's supposed to mean that we're going to see more numbers instead of default set. But I think this is already long, so maybe it's set by default. But never mind, I'm just going to set it at format long. I'm going to type that again and show you what I mean. Yeah, it's the same. Yeah, so this is actually the format long, so we can just ignore this. I think it's set by default. I'm just following the code in the example. Okay, so now we get the B1, which means that it is y equals to B naught plus something like 0.000137 x, where 0.001372 is this B1 here, that we got this from this calculation x backslash y to find the slope. Okay, with that, let us calculate the model, because the first model we're trying to build is without intercept. So it should be y equals to, let's say we assume b naught is 0. This is just an assumption. So let's say 0, then plus 0.000137 x. So if we want to recreate that linear line that is plotted through the points, then it's just a matter of, be very attentive of this. let's say we calculate it, that B1 that we calculate times with the X value. See, this B1, 0.001372, we times with the X value. What is X? X, remember, is this one. Once we multiply this slope that we calculated using this and we multiply it with this X value, then we should get that model value, that straight line value. Okay, so if I just suppress this, and now we have the Y calculated one value. And from here, let's plot that. Okay, scatter. This is another way to plot. Scatter, let's see, X and Y. Just now we used the plot, but now it's this one will also do the same thing, except for it uses the, if you notice just now, the plot uses a line plot, but if you use scatter, it becomes a, what do you call that, dot plot. Not a dot plot, it uses that circle instead of a line. If I press enter here, then you see, okay. So this is the plot that you saw just now, X versus Y or Y versus X, population versus, traffic fatalities versus population. We see that there is something, now we want to build a line through it. Now that equation that we use, the Y calculated 1 equals B1 minus times X here, this is that line that's supposed to go through here. So let me just type that in. Okay, this is a list of code. So let me just copy this. I think it's a lot easier if I have to copy this, and then I would explain one by one to you. I don't like to write the code straight away, or because if I do that, then you might be confused with so many things at once. So this is the reference I'm going to use, and then this is the part where we will do it interactively. So scatter XY, we plot X versus Y, population versus traffic fatalities. And then we're going to add all these, actually we already did the model, it's just that we want to visualize it right now. So this part here is the plotting part. So I think you've learned this, hold on. Okay, when we say hold on, that means you hold on to this. We're not going to plot anywhere, any new plot. We're just going to, all of these things would be plotted here if we use this hold on function. So once I press this hold on, nothing will show. Okay, it will still be like this. Nothing will change, but then everything that we add will be added to this plot here. Okay, next is let's plot this. Okay, I'm going to type it better. Okay, plot X as the x-axis and the calculated values. We plot this on that plot just now. So press enter. Just now we plot X versus Y. Now we plot X versus the model that we calculated. Now we see that line there. Okay, this is that Y calculated 1 value. And why is it line? Because we use plot. If we use scatter, it would be a scatter plot. Okay, so far so good. Hello.
Yeah, still okay.
Yes, Doctor. Okay.
Okay. Emma, I'm gonna share with you the recording of the video so you can rewatch it, and then you can slow down if you want, and I'll give you the website too, where I used to refer this. So for now, just try to follow the logic, if not to memorize, okay? And then okay, now this part here, X label, Y label, these are all just to make the plot looks better, right? Because right now the plot just look like this, right? Let's say you want to show that you already developed the model, the linear model, and then you want to export the figures so that you can put in your report. Of course, you need to put the labels and all that. You cannot just put it like this. So that's why we need to add all this. So to add labels is just this, X label, press enter. Let's see the output. There you see population of state. And then Y label, fatal traffic accidents per state. I can just copy this. Okay. Press enter. And then you see that. And then the title. So I copy this. The title goes here. Then I paste it here. There. And then grid on. I don't really remember what grid on means, but let's try it. So I press type grid on, press enter and see. Oh, the grid means that it draws the grid on the plot. Okay, so those are just plotting out linear regression. The linear regression part is already done. It's actually quite simply, it's just this part here. This is the linear regression part when we calculate the slope. Now, this is the model if we assume that the slope is going through zero, okay? Which is a fair assumption to make too, because it looks as if it goes to zero. But let's say you want to make, you don't want to make that assumption. We want to say that there is a B naught value. There is a value, it's not zero. It's something like this, where B naught is a value. So to do that, in Matlab, then we use another set of code. Let's see. Oh yeah, there it is. Now we need to come up with two values. Okay, one value is that x value that comes with the slope, and the other value is that intercept value. So we create another matrix, okay, X, and in that matrix, I hope you still remember this. Once means to create. Okay, let me just do this step by step so that you'll get lost. Once is a function, creates the number 1 for the length of x, and then we close. So if I press enter here, then you will see the output here. So we want to create a vector matrix of all ones, and how long is that? It is the length of x. So what is the length of x? So let's see, looking at here, x is 51. So that means you want to create like 1, 1, 1, 1, 1, 1, a whole column of it with the length of 1. So if I press enter here, then you should see that, okay? All these ones, and these have 51 values in it. This is just a placeholder. It's something like a, we need to put it here so that we'll be able to get the y-intercept. Okay, then coming to this one will create that one value, and then 51 one values, and then another is the x value, and then we put it inside this matrix and we put it inside x. So let me type that in earlier. So this is now capital X, not small x, equals to ones. This is the first column, x 1, and then the second column is this x. What is this x here? This x is here is this x value. If I double click this, you see this is the x value. And then we put it inside this matrix called capital X. Then I press enter, then you see the capital X now. Notice there is a difference. One is a small x, one is the big X. But notice that the big X has 2 columns in it, while the small x has 1 column in it. If I double click this, then you see the first column is all 1, like what I said just now, 51. The second column is the x value. Now we recalculate the B1 here. We recalculate B1 here, and we recalculate B0 here. X backslash y. Now remember, this x here has 2 columns in it, and because it has 2 columns, it will be able to calculate that y-intercept. So this is a new B. Just now, the old B was B1, but this is the new B that has the slope and the y-intercept. So you see there, this is the y-intercept, while this one is the slope. Okay, notice here is 10 to the power of 2, which means that it's 10 to the power of -2. So this just tells you that this is not, it's not 1.42, but it's actually 0.0142, and this one is not 0.000 with all the zeros here. It's to the left by 2 decimal point because of this. So this B here contains that y. Oh, sorry. Actually, it's not 2 to the left. It's actually 2 to the right. So instead of 1.42, it's 142 because it's 10 to the power of 10 to the power of 2. And then the y slope is not 0.0001.25, it's 1.25. I think it's just bring that 2 decimal point here to become slightly bigger because of this. Okay, if I double click it, then you can see it. Yeah. All right, there it is. Now we have that the y-intercept and also the slope. then we can, let's see how it performs now. Y coefficient 2 now, just now was Y coefficient 1, with the two values, the slope as well as the intercept. So we multiply with x. Remember this x here is the two-column one with all the ones, and the other is the x value. Multiply it with the b, the new b that we calculate, and I want to suppress the output. Now we have the y coefficient 2. So this is the other model, the model with the y-intercept. Just now was the model without the y-intercept. And then the next set of line is actually just to plot it. Let's plot it. So plot x. Okay, why is it not capital X? Because this capital X has two columns, but in the end we just want to plot against just one X. So that's why we just use this X instead of capital X here. Okay, so X, and then the y-intercept, the y value is y function 2, and then this part here is just a dashed line. Instead of a solid line, we want it to be a dashed line. And then close, and then we press enter. Okay, notice here, this is just one solid line. Now, once we press enter here, then you see that new model fitted using the intercept. So it's slightly, if you zoom in here, you notice that this dashed line here is slightly above because of the y-intercept. But this line should be better fit than this line here that assumes the y-intercept to be 0. And then we add in the legend. So to add a legend is actually quite simple. It's just this. I think I'll just copy this here and paste it. Make it a bit bigger. You can see. Press enter. And then you see the legend there. So the data 0 here, and then the slope, just the slope only, while this dashed line, the slope with the intercept. Okay, why we're able to add all these things to the plot just now? Because we add in the, where is that? Yeah, this part here. We add in the hold on top before we actually do all of this. That's why it's able to keep on adding the material onto the plot. So that's it. That's actually linear regression using Matlab. And then actually you can do this in Excel too, but Excel has less, it's less accurate and it has less information in terms of reporting the linear regression model. There are certain things that we can do in Matlab. For example, calculate the residuals and calculate whether the residuals are concentrated in a certain area or not, which you cannot do in Excel. A quick and easy way for us to get linear regression is, of course, you can do it in Excel, but then Excel doesn't work so well with large sets of data, and it's not able to display all the extra information like the residuals that you can actually calculate using Matlab. And then we have now we want to compare the R square. Do you know what R square is? Maybe anybody can volunteer to respond. Have you ever heard of R square? I think in Excel, when we plot, then we can just tick R square, it will show us the value, right?
Yeah, is it the regression?
Yes, the coefficient of determination. So now we want to compare. Yeah, thank you for that response. Now we want to compare the R square for the one without assuming that the intercept is 0, and the second is the one we assume that intercept is not 0. So these are the equation. It looks complicated, but I'm sure you've seen this before, and you calculated it using by hand too last time in secondary school, even, where you come up with a table, you x times y, then summation of x, y, and all that. I hope you can recall that. So this is actually much simplified in Matlab as long as you know the code. For example, here sum y minus calculation 1 square divide by sum y minus min y square. So that's just the formula of R square 1. But this is for the model without the intercept, while this one is the model y coefficient 2 with the intercept. So let's see how they perform, just out of curiosity's sake. Oops, sorry. Let me just select this. I'm not going to type all of this, but I think I explained it just now, so I hope that by now you know the logic behind this. Okay, we press enter. Okay, the R square for the assumption that The y-intercept is 0 is 0.822. It's quite good because we can see that the data is quoted, and the model developed is also can fit the data well at an 82% level. Okay, and then if we assume that the intercept is not 0 for the second model, the same equation, except for now, instead of y calculation 1, it's y calculation 2 here. I press enter, it's 0.83. So it's slightly better than the one assuming that the intercept is 0. So one thing I want to mention about R square here is that it is different than the correlation coefficient. Okay, this one I want to stress. Let me write a note here at the top so you can see. By the way, this is not an actual script because we're not being very strict on the code, but this is just meant for me to as a note for you to read. So there's a difference between correlation coefficient, ignore the color, and the coefficient of determination. Where correlation coefficient is small r, and coefficient of detection is capital R but square. I cannot square this, so I use this cat symbol as a substitute. Do you know this difference? Anybody? Do you know that these two are different? Yes, no?
Yes. I know that there's a difference, but I kind of forgot what's the difference.
Yeah, it's actually a very big difference in terms of interpretation. That's why I want to mention it right now, although you actually studied this many times already. So correlation coefficient goes from -1 to +1. Okay, where if it's like -1, it's negatively correlated, which means that if one would affect the other parameter, one parameter would affect the other parameter inversely. While if it's close to +1, means that one would affect the other parameter positively. Like for example, the correlation coefficient for this one would be quite close to +1 because as one increase, this population of state increase, the fatal traffic accident also would increase. But like imagine that the data looks something like that, means that it's close to -1. But it just shows the correlation, and it has nothing to do with the model. Now, what we developed here, the line here that we've come up with, that we draw for the data here, is not correlation coefficient. This is the linear regression model. So be very, very careful with the terms you use because it would show how well you know your statistics if you you use these two terms interchangeably. It means that you think they're the same. I can understand why you think they're the same. It's because to go from this r value to r square is just square. You just need to square it, then you get the r square value. For example, if the r is equals to 0.5, then your r square is 0.25. You just square it. Yeah, is that correct? No. Wait. Not zero. It's not. It's correct, right? Yeah, 0.25. So you think that these two are the same, but again, correlation coefficient is meant to show how one affects the other, whether there are correlation between two variables, while the coefficient determinant is actually more towards the model developed. So for example, this model here, right now is 0.82. It's a good model because this model is able to explain the data up to 82%. And then it's not able to explain the data as much as 18%. That can be said about the coefficient of determination, but it cannot be said for the correlation coefficient. The correlation coefficient can tell you whether they are positively correlated or negatively correlated only, and doesn't tell you anything about the model. While the coefficient determination tells you how well the model that you've developed here is the data. So if it's at 82%, means that it's able to describe the data 82%. That means this population state is able to describe the data 82%. But if the second model is able to describe the data 83%, 84%. But keep in mind that there's also 16% that the data is not able to explain. 16% more that's not that this population state is not able to explain. If the R square is 100% or 1, then means that this variable is able to explain, the model is able to explain the effect of this variable on this by up to 100%. It's perfect. But usually if you collect two raw data, like for example, this is a raw data by itself, you collect it in a different way, while this is collected in a different way. I don't think it's ever been done where you can get 100% model developed, especially if you collect in two different ways. This is probably being collected by census, by surveys, while this is measured by the police, who records all the fatalities on the road. So two different lines of measurement, but they correlate. So that's the reason why it doesn't go up to 100%. It only can go up to 100% if you use an equation to come up with the model. Obviously, it will be 100%. That means if you have the equation y equals to 2x, then you plot it and you draw this line, of course, it's going to be 100% because x is calculated here. So that's the only time when it becomes 100%, but any other times it's not going to be 100%. Okay, so far so good. I think I'm spending too much time on linear regression.
Yeah. I have a question.
Yes, please.
Regarding the coefficient of determination, is it the same R square with the one we use in Excel?
Yeah, here's the same.
Because after we R square, normally it won't have negative, right? But sometimes like in Excel there will be negative.
No, it cannot be negative because you square. Any value that you square will be positive. Right?
Yeah, but then sometimes I just don't understand why the Excel R square will come out like negative value.
It might not be coefficient of determination because mathematically it's impossible to be negative because anything that you square should be positive. You might mistaken it with correlation coefficient, which can be negative.
Okay, I see. Okay, I see. Thank you.
Yeah, correlation coefficient, then it can be negative. Okay.
Okay, doctor.
Yeah, so these things are actually some you should already know before, but I think it's good for me to explain it to you in a different manner so that you get a better understanding out of it when you listen to it many times, right? And also from different perspectives. So that's okay. That's on linear regression. Now let's go to the main topic of the class, which is the multivariable linear regression. The good news about multivariable linear regression is the same concept, except for we extend it to more than two variables. But the idea is the same. Even the equations are about the same too. So let's do this in Matlab because you cannot do multivariable linear regression in Excel. So let me clear all. No, I'm not sure whether let me clear this first. Okay. Put down here. Let's set this up. And let me clear this. And then clear this. Okay, start from a clean slate. On a clean slate here. And okay, let me close this plot. Oh, I forgot to hold off just now. Just now we hold on, now we should hold off. But we already closed it, so never mind. Okay. Now I'm gonna copy that code and put it there, but I'm going to go through it step by step so you can understand. This is the code. Let me paste it here. Okay. So if I have to show you just straight away, then you might not be able to understand because so many things going on at one time. So I'm just going to go through this step by step. Now, in this multivariable linear regression example, we're going to use this data set called car small. This car small is actually a very popular data set used in many demos because every time we show something, we cannot be expected to collect data at that time and then run a demo on that data. So it's not possible. So that's why we would use this data set that's built in Matlab. And this particular data set, like I mentioned just now, this car small is very popular. It's even available in different softwares instead of just Matlab. So let's understand a bit. In here, as written in the name, car. So it's something to do with car. So these are car data acceleration. Let's see. There's 100 rows. I think this is the top acceleration value. And then cylinders is the number of cylinders for the car. Some of it 8 cylinders, some 4 cylinders. I think those car buffs would probably understand this. I'm not a car buff myself, but I have some idea of what it is. So it's just the number of cylinders in the car. And then the displacement, I think something to do with the engine too. Okay. Horsepower is I think miles of fuel per miles per gallon, I think. It's just the mileage or how much the car can run with a certain amount of fuel. The model year, this is miles per gallon, correct? I think this is manufacturing, although I'm not really that sure. Let's see. Oh, I think, okay, mind, we just ignore this for now. It's not, I don't think it's going to use anyway. So the model here is the model car, okay? Model and also maybe the brand. This is something to do with that. The model year is when was it built? I think this is a very old data set. This is 1970s, 1976, 1982. Then this is the miles per gallon. Some of them are not available, NaN, not a number. Origin is where it's built, US, Germany, France, okay. And the weight of the car. I'm not even sure this is kg, maybe it's pounds or tons, I don't know. But we're not interested with the actual value, we're just interested in using that multivariable statistical tools on this data set. And we use it on this data because we have many parameters to test. So as you can see, we have 1, 2, 3, 4, and 5, 6, and 7. Okay, how do I know? Because I look at this, there's this symbol here, matrix symbol means that these are data. Well, this is actually data, but these are character data. So if you want to run multivariable linear regression and also linear regression, we have to work with numbers and not with characters. So yeah, we have so many, but we're just going to use 3, and we're going to relate 2 variables, the predictor variables against the response variable, the y-axis. So 2 x-axis values and 1 y-axis values, one y-axis value. The one here we're going to use is weight. X1 equals to weight. I'm just going to type in. I could just use y weight here because the weight is there. I could straight away use weight, but then I think just to make it easier for us to see that we're just working on this x1, x2, and y2, that's why they substitute this weight with x1. So when I press enter here, then this x1 contains that weight value. And then x2, the second predictor variable, is horsepower. So we have x2. Just keep in mind, this x1 is the same thing as weight, and this x2 is the same thing as this horsepower. Again, we do this because it's easier for us to work with this x and y instead of trying to remember which one we're using. And then y, this is the predictor, right? What's the term again? Let me check. There's a term that we need to use when we conduct linear regression, the predictor and response. Okay, so this x1 and x2, these are the predictors. That means the variable that we use to predict the response, in this case, is y, miles per gallon. So we have 2 predictors and 1 response, and it's already declared in the workspace. Then similar to just now, we have to set up the matrix. So let me walk you through this. We have ones. I hope you remember the definition of ones just now. And the size, we want to create a vector of ones, a series of 1 value, following the size of x1. What is x1? X1 is weight. So x1, there's 100 values. X1, then close. And then we put x1, x2, and x1. times x2. I hope you remember this is element by element multiplication. That means we just want multiply the first element of x1, multiply the second element of x2. Sorry, first element of x1 multiply first element of x2, second element of x1 minus x2. Just element by element. Then we close it. Now, once I press enter, then we get the new x value here, capital X. Let's see what's inside. In the first column, as expected, are the ones generated by that ones function. How many are there? We have 100 ones, right? Because it follows the size of 1x. And then number 2 here is the x1, which is the weight. Number 3 column is the horsepower. Number 4th column, this is, we're not going to use it later, but in multivariable linear regression, we have like singular predictors. Like this is singular, x1 is singular predictor here, but we can also have a combination of predictors, like say x1 times x2. So again, there's still 2 predictors, but then there is a combination of 2 predictors here, which you can do for multivariable statistics, a multivariable linear regression. Like say, imagine that there's another one, x3. And then now it becomes, it can be x1 times x3. It could be x2 times x3. So any combination of these 3 here can be added up as one of the columns, but we're not going to go up to that, and up to that, we're just going to go up to this for now. But just keep in mind that you can actually combine the two, because, okay, maybe x1 has a relationship with y, maybe x2 has a relationship with y, but maybe the combination of x1 and x2 also have a relationship with y. So that's why this one is written there. Okay, and then you can see here. So the second column, third column, we multiply, so you get the 4th column here to just guess that there could be a relationship between x1 and x2, although there might not be also. Now, we calculate the b. Remember the b? So the b here, let me see. How do we extend? I hope you remember me show it to you again. This is the equation for simple linear regression. For multivariable linear regression, it's just b0 plus b1x plus b2x plus b3 x1 x2 and this one x2, sorry, x1 times x2. So notice the similarities. That's what I mean by it's quite simple to extend, because the b1 is still there, the intercept. And then before that, it's just up to here. But now when we have 2 other variables, then we just need to add one more, the coefficient b2, and then the interaction between the x1 and x2 here, the combination of x1 and x2, and the b3 is the coefficient for these. So when we run this code here, regress y versus x, so x we have 1, 2, 3, 4, 5. Basically, this is it. This is the one. 1, 2, 3, 4. So we have like 4 coefficients: b0, b1, b2, and b3. So once we run this, then we calculate that. So let me do that now. We put it inside b. We use this function called regress y, x, and press enter. So remember, I mentioned there are 4 coefficients: b0, b1, b2, b3. So there it is. This is b0, b1, b2, and b3. You can sort of imagine it to be the developed equation is y equals to 60.7 plus negative 0.01 x1 plus negative 0.81882 x2 plus b3 is 0.0000383 and this is the x1 times x2 predictor. That's the equation for 2 variable predictors. Okay, now let's plot it. So actually, the regression part is already done. These are the model. You already developed the model already. So when you write it something like this, means that you've already done multivariable linear regression, but it's as easy as that. It's just running the code, just knowing, arranging it and running the code, and you already developed the model. And it, like say the question is, develop the model, the multivariable linear regression model for these parameters, and then you did the code, and then this is the model, this is the answer. But we like to view how it looks like. So lucky for us, since we only work with two predictors, we can still view it in a plot, but it's a 3D plot. But anything more than that, we cannot plot it anymore. So if it's more than two predictor, then we can only resort to just reporting the equation. We cannot show the plot because we cannot plot 4 dimensions or 5 dimensions. Okay, coming back, let's plot it. So again, we use scatter, scatter 3D. Just now was scatter 2D, so scatter 3D. Okay, x1, the first variable predictor, x2, and then y, and then I think this is just a way to plot it. It's a fill point, and I press enter. So that's the 3D plot there. So we can view how it works for that. So that's the cool thing about Matlab too, because you'll be able to view in 3D. And then this is one of the predictors, and this is the other predictor there. And we sort of see the three-dimensional relationship between the predictor and the response, right? Can you see this?
Yes, we can.
Yes.
Okay. All right, so next up, I put hold on so that we can add more features to the plot. Again, hold on doesn't do anything. It just like holds this figure in place so that we can add in more things inside. Okay, these two things here, x1 fit, minimum x2 fit here is just to fix the y-axis so it doesn't run off. Okay, so let me just type it, and then so you can follow along. X1 fit equals to the minimum of x1. So this function goes inside x1 and find the minimum value, and then it increments by 100. Like say the minimum value is 200. So the next value is 200 plus 100, 300. Next value is 400, 500, 600. So the increment is 100 until the maximum of x1. So this is just to come up with a list of values that goes from the minimum to the maximum at an increment of 100. So press enter, and I see an x1 fit here. So the minimum was 1795 in x1, and then adds up 100, 100, 100, 100, 100 until the maximum, which is 4695. This is not actual data. This is just to set the x-axis, the minimum and maximum axis, values for the axis. And then we do it for the second, because you remember there's one here and then there's another one here. So one of it is x1 and the other one is x2. Same thing, min x2, but now I think the increment is 10 and the maximum is, okay, let's do that. Now you might wonder, how do I know this is 100, this is 10? I think this comes from experience. When you plot and you notice that the plot looks weird, so we have to change the increment accordingly. Okay, so once I press this 2 here, nothing changed here because we're just generating the x1 and x2 value here, okay, to set up for the plot later. Next, we develop the mesh grid because we need to get ready the canvas, the place where to plot. I know that we plot here just now, but this is meant for the 3D plot for now. So we're going to get ready the plot by, this is another variable, x fit, x2 fit. This x1 capital fit and x2 capital fit, it's not the same as this. This is another generated variable. And then these are case sensitive. So we know that these are different, but we know that this is relating to this, but they are different. Okay, equals to, this is the mesh grid. We develop to create the mesh. And then we use the x1 fit and x2 fit value. Just like this now, this is just meant to create the canvas for us to draw the plot in. So once you press enter, we have x1 fit and x2 fit. So you see there, x1 fit and x2 fit. Okay, notice the difference. If x1 fit is just 1 times 30, which means that it's 1 row with 30 columns, while x2 fit is 1 row with 18 columns. If I double click on this, you see one row, but we have 18 columns. And x1 fit is 1 row with 30 columns. Okay. And then, but now, why do we do this? So that we can create that mesh. Okay, now we see x1 fit. What's inside x1 fit? So it becomes like a matrix now. You see? It is 18 by 30. Why we need to do this? Because if we want to plot 3D, we cannot plot it. We have to develop the 3D grid first. So this is the 3D grid, the x1 fit and the x2 fit. This is the 3D grid for us to plot our 3D plot. So that's the extra thing. You might think it's quite simple to go from 2D to 3D. 2D is just we have the x-axis and the y-axis grid. But in 3D, you need to develop that block of values for the x and the x1 and x2 and also the y. So that's the step that we're doing here right now. This step here is to draw that block. Not to actually plot, but actually to get ready the place for us to plot. And then we write the model. Okay. So this model here, okay, it's too long for me to type, but let me just explain. So this B1, what is B1? So this B, remember this B here? Okay. So 60. So this is the first row. So we use this one, the coefficient. This B2 is the second row. This B3 is the third row. The B4 is the fourth row. And what is this x1 fit? X1 fit is that value that we created. It's not the plot. So B1 doesn't times with any variable. So that's why it's times 1. There's nothing here. Not 0, but 1. X1 fit is that axis that we created just now. X2 fit is the other axis. And the B4 is the X1 fit times X2 fit. So this is actually the model. We're trying to plot the line or the plane model. So copy this. And let me close this. Paste. Once I press enter, Y fit would be, the model will be calculated. Y fit. Notice that it's 18 by 30. And then now is the fun part where we plot that model. So we plot it using mesh. Mesh is like scatter plot, but it's for 3D. So X fit is the first variable, then X2 fit, X2 fit, and then the Y fit. Then we press enter. Let's see the output. So that's it. You see? That's the 3D model. The 3D model, and then this is the plot, the 3D plot, the scatter plot, and this is the model that we developed using multivariable linear regression. So notice that if it's only linear regression model, it's just x versus y, it's just a line. But if it's a multivariable linear regression, like 2 variables, it becomes a plane. And if it's a 3 variable, it becomes an object. So that's why it's difficult for us to plot anything more, because we need to have another axis for us to plot the 4D, which we cannot visualize. As human beings, we're not able to visualize 4D. And then we just add the label. So here it says X label, weight, horsepower. I'm just going to copy this, because right now there are no labels. Oh, sorry, 3. Oh, I'm really behind schedule. There's no label here. I'm going to paste it here. Now we see the label, weight, horsepower, MPG. And then this part here, view, is just so that, okay, let me just show side by side. This is something we change, right? So if you put view 5010 here, you press enter, notice that the view changed to the part where the view that we want. So of course we can change it using the mouse too. And then to break off the connection with the figure, then we pull off. So that's the developed model. The developed model for that 2 predictors on MPG. So we see that there is a relationship between horsepower and weight on the MPG, which makes sense because if you have more horsepower, if you have more weight, then of course the miles per gallon will also increase. I mean, the heavier the car, the more powerful the car is, the more fuel it consumes. But then it also shows that these two predictors are needed to make a better prediction on the miles per gallon. If we just use one, like say weight against miles per gallon, then it might give a model too using linear regression because it's just two variable, but it's not going to be a very robust model because it doesn't account for every other predictors that could affect the miles per gallon. Okay, so I think I've been talking for 1 hour nonstop. A bit tired about that, but how about everyone? Are you able to follow along? You understand?
So far can understand.
Okay, that's very good. Now I'm not sure whether this topic will be in your exam or assignment. Is it going to be in your exam or assignment? I'm just a guest lecturer. I don't teach this course. I mean, I'm one that gives the assignment or test. Do you know?
We're not sure about that, Doctor.
I don't think so because if I teach, maybe this is an extra topic, so it's not something that's I think should be in the assignment or in the test. But it's useful for you to know so that you can go beyond just the normal linear regression that you're used to. So you might still think that okay, we can use Excel for linear regression. Yes, you can still do it. It's just the simplest, the fastest way. But again, it doesn't have the enough tools in it to calculate the residuals, which I did not cover. I didn't have time to cover, but there is that tool to calculate the difference between the model and the point so that we know the residuals, the difference, which can help with model evaluation. So that one cannot be done in Excel, but then if you just want to get the R squared, the R, and the model, you can do it in Excel. But anything beyond that, then you cannot use Excel. You need to resort to Matlab or to R because these softwares will have many tools in them to help you with the visualization. I'm sure Matlab, I don't think Excel can do this to come up with a model and to plot it. Oh, by the way, if you want to export this plot, you just click on File and then you click on I think View, select File, New, and then Save As. I think it's Save As, and then you can save it like either bitmap or JPEG. I think JPEG, and then you can put it in your report. Okay, I'm not going to save this. So that's it. I know some of you have left because maybe they have class. So I can stop here. But before that, let me ask if you have any good questions for me.